Howdy, everyone, and welcome back to my channel. I am Professor Parks, PhD, and this is yet another one of my installments in my lecture series on the solar system. I decided to go live a little early because I'm just chaotic. if you haven't figured that out by now, then you obviously haven't been paying attention to my channel. But anyway, thank you for being here. For those of you who are watching in the future, thank you for watching. Before I get started with today's lecture, which is on the search for alien worlds, as it were, or exoplanets, as we say in the biz, I just want to plug the event for tonight. We have our Evening Under the Stars public event is tonight here at George Mason Observatory. Let me pull up that website again. And share it. It's Evening Under the Stars. And I will copy and I will put this in paste. Put that link there. And I will stop sharing that. Share screen. So, a talk. So you may. So if you're familiar with my channel, you're probably have heard me plug this on a couple of the different occasions. So every semester, fall and spring, we do a Evening Under the Stars public event series here at George Mason Observatory. And due to the pandemic, we have now moved from an in-person experience through a virtual experience. Now we are doing hybrid, or we are trying our best at doing a hybrid experience, although it's been challenging to say the least. Evening Under the Stars is a combination of a talk by an astronomer or someone closely related to the astronomy field, and a tour of our observatory. So obviously the best experience is obviously if you came to our observatory in person. But again, like I said, we do offer a virtual event, and you can do that through Zoom. There's no registration. There's no nothing. You just click on that link, and you will see my shining face as the MC of the evening. The speaker will start the event will start at 7. I will give a brief spiel, and then our speaker will take over, give about a 45-minute talk plus Q&A, and then we will transition over to the telescope. While the in-person folks are walking over to the observatory proper, one of our tour guides will provide a virtual, essentially, session with our telescope. It's actually looking, I would say, beautiful, but considering it's currently 80 friggin' degrees, or 13 for those of you who are not Imperials, and for me that is just depressing. It is very, very hot. I don't like that summer is coming. Winter should come, and it should stay here all year round. That if I were a Bond villain, that would be my evil plan, is to somehow alter the Earth's orbit such that it is winter all year round. Hey, Peter, howdy. Anyway, so our speaker tonight has had his fair share of controversy, or at least in one particular area. He is controversial in his views on the JWST, but he is not going to be speaking about the JWST. Dr. Hakeem Alusier, who is becoming quite the science communication celebrity, is a Robinson Fellow visiting professor here at George Mason, and he's going to be talking about the sun. His field of expertise is actually in cosmology. He has previously given a talk for us about the evidence surrounding supporting the Big Bang. It was a fantastic talk. He He is an excellent speaker. Highly recommend coming tonight and either in person or virtual to experience this. If you are watching this late, what I will be doing though is I will be recording this event, particularly the talk, and I will be uploading that recording up to our George Mason Observatory YouTube channel, and I will also be snipping out the talk itself and uploading that to my channel, assuming that I have the free time to get that in. Anyway, but like I said, Hakeem is a fantastic speaker. I'm sure that this is going to be a great talk on the sun, and basically he's just going to talk about what it is, what it's made of, how it works, that sort of thing. So it should be. I am very much looking forward to it. If I am, to be honest with you. All right, now let's go on with the lecture. Howdy, Real Cygnus. No, you are not too late. All right, so where we left off last time was I was talking about the solar system, and really where I was going was as a whole. Really where I was going was we want to try to find an idea or find an idea or really create a model or understand really how the solar system came into being. In order to do that, you basically have to put constraints on the problem. Essentially, any theory or any model that you create of how you believe something came into existence has to what's the word I'm looking for? Man, I'm losing all my words. Basically, when you run that model over time, from a starting point, run it over time, about 4.5 billion years from now, that model should reflect what we see in what we see in our solar system today. So we need to understand our solar system as best we can. And so the previous lecture was talking about the fact, just the broad strokes of we've got, I am contractually obligated to say 8 planets. We've got dwarf planets. We've got asteroids, comets, and so forth, all in various regions of the solar system, all with various characteristics in terms of their mass, their density, their eccentricities, all that. And any model has to explain all of that. Basically, it has to be able to explain why, for example, Jupiter has a mass 300 times the mass of the Earth and has a very low eccentricity, low inclination orbit as compared to, say, Pluto, which is much less massive than the Earth and has an eccentricity that is much higher, around 25%, 0.25 eccentricity or inclination, about 15 degrees. Honestly, I'm pulling those numbers out of my butt. But that's what Google is for. You can Google the inclination and eccentricity. The point is, Jupiter is very massive and has a very, very well-behaved orbit. The orbit is nearly circular, and it's nearly in the same plane as the ecliptic. Whereas Pluto is much, much smaller, much further out, and its orbit is less nice. It's more eccentric, and it is more inclined. Hey, Ord, Florida. Howdy, y'all. And we thought we had this. We thought we had this idea down of how the universe or how the solar system came into being. Actually, Immanuel Kant was the first one who really came up with this idea that the solar system sprang into existence from a massive interstellar cloud of dust and gas that collapsed in and upon itself. But for a very long time, we only had one data point in which to really constrain, like I said, this model, to constrain the idea of if we have certain initial conditions like the mass of this cloud, the speed at which it rotates, all the size that it originally starts off with, will it eventually collapse down and actually represent what we actually see in the night sky or in reality around us? Well, like I said, we only had one data point, which is from a scientific standpoint, That's kind of a good or bad thing because, as I said in the last lecture, one, it really nails down, really does constrain things in the sense of it's a binary switch. It either works or it doesn't. But what it doesn't do, what it does not constrain very well, is the weird stuff, as I like to put it, the stuff that you really weren't expecting. And boy, when we looked for planets around other solar systems or around other stars, boy, did we find the unexpected. Now, I'm not going to get into the first exoplanet that's discovered because honestly, it's really weird, and it really doesn't mesh well with this discussion. The first planet was actually discovered around a pulsar, which is a stellar corpse. And yeah, finding an Earth around a dead star was unexpected, to say the least. But what we're trying to do is we're trying to figure out how our solar system came into being, with a sun, particularly for stars that look very much like our sun, or what we call sun-like stars, which is a very kludgy sort of classification of stars that basically are the same, similar mass, similar radius, similar luminosity. It's really kind of hand wavy as to what sun-like is. But anyway, so in 1995, though, let me stop that, and two wonderful scientists put out that one in Nature, in the publication Nature. They put out this paper. I apologize for my logo. The title of the paper is "A Jupiter Mass Companion to a Solar Type Star" by Michel Mayor, and I am going to butcher this name. Didier. No, I'm not going to butcher it. I'm not. No, Q. I'm just going to call them Q. I don't even know where to begin to pronounce that name. Anyway, to give you an idea of just how monumental this was. So not only did we find a planet orbiting around a star, orbiting around a star not like this, or orbiting around a star that is not the sun. So we have essentially very strong evidence that we are not alone in terms of stellar systems. I mean, yes, we did in 1992 we found that weird pulsar planet, but now we have something that basically we can really hang our hat on, that there are solar systems beyond our own. That we no longer have a data point of one. But the surprise came into it in just what we found. And to give to really put the spoiler to it, oops, this is not true. I won't dive into this paper. Maybe I'll do an entire show on just this paper or very similar papers. I don't know. Anyway, so what they did was they used a particular technique called the radial velocity method, which I talked about in, I think, my very first lecture, and which I will also revisit in a few moments. They use a very specific technique, looking at the light of a star, of the star 51 Pegasi, which basically means that it's the 51 brightest star in the constellation of Pegasus, roughly speaking. That's what the designation stands for. So they looked at 51 Pegasi, and they looked at the light from that star, and they noticed that the light from that star periodically blue shifted and red shifted over time. And from that, they were able to extract that the star itself was moving towards and away from us at a fairly small rate of speed. And the reason for that, most likely, again, it's, we don't prove things in science, but the most likely explanation is that there was a gravitational tug on, or that there is a gravitational tug on that star, causing it to wobble, and that gravitational body was in fact a Jupiter mass planet with an orbital period of 4.2293 plus or minus 0.0011 days. All right, so the mass of this thing is estimated to be about half of Jupiter's mass. Again, or more specifically, about 150 times the mass of the Earth. Its orbital period is 4 days. From what Newton's revision of Kepler's law tells us, is that its position has to be 10 times closer to its host star than Mercury is to our sun. So we're finding basically a gas giant, and this thing has been studied just to death, and we are very confident that this is in fact a gas giant that is surviving the massive amount of radiation that it's receiving. It is a gas giant that is roughly, with a surface temperature roughly about 15,000 Kelvin, or 1500 Kelvin. And it is there, and it is orbiting very, very close to the host star. The model of our solar system, which was developed in Nice, France, which is why it's called the Nice model. The Nice model did not anticipate this. There was no mechanism in the Nice model to account for the fact that you would find a Jupiter that close in. Now, the reason for that, we'll get into more when I actually talk about the formation mechanisms, or how the solar system came into being, or how planetary systems came into being. But ultimately, the simple answer is that it's far too hot for a Jovian planet to form at such a close distance to its host star. So something else must be going on. And this isn't the only oddball that we've found. Now, I hope you will forgive me, but I'm going to sort of diverge off of the course material for a moment. Share the screen. That one. And really, because I think that the subject of exoplanets is a great way to look at science. It's a great way to talk about various different aspects of science. This is the NASA Exoplanet Archive. This is basically the Americans' archive. If you don't trust us Americans, and you want the European version, then you want to go to exoplanets.org, the ESA. I always get ESA, ESO confused. I think it's ESA. The ESA runs that one. But this is the American version, run by IPAC, which is the Infrared Processing and Analysis Center. This is our archive of the number of planets that we have confirmed and the number of planets that we suspect are out there. Again, I'm not really going to get into the specifics of what a confirmed planet is, what a candidate planet is, but just want you to know that a confirmed planet is essentially something that we have very good confidence that it exists. A candidate planet is, we suspect that it's there, but more observations are needed. This is something that changes almost daily. You can see that with the confirmed planets, we now know, or we now have strong evidence for 5,322 planets as of March 29th, 2023. If you were to come back in a week, that number is going to change. I would put money on it. This box says TESS confirmed planets. TESS is a satellite very much like Kepler, which relies on the transiting method to find things. And again, I will get into that method very, very shortly. And then over here, you have that there are 6,237 TESS candidate planets, or TESS objects, TOIs, TESS objects of interest, something that we here at George Mason are involved in is we look at these candidate planets and we try to provide observations that will change them from candidate to confirmed. But again, don't really want to get too much into the weeds of this. Just want to, if you want to, I wanted to go to generate plots. Now I'm going to bring this one up. Okay, that one did not share. Let's try that again. Presents, share screen. That one. There we go. So this is, and you can see again, my logo is blocking it. But in the upper right, the corner, it says that this plot is current up to March 31st, 2023, and this is only confirmed planets. And yes, Clive, we didn't actually. We didn't have to delete Alderaan, but we did have to delete Vulcan. The planet Vulcan is no longer there. So, but that's another story for another time. What this plot is, other than messy, is a plot of mass on the y-axis and a plot of period on the x-axis. And the different colors correspond to different detection methods that we have used. And you can see right off that the two major methods, the workhorse methods that we use are what's known as the radial velocity method and the transiting method. But you also have microlensing, you have direct imaging, you have timing variations, you have orbital brightness modulation, you have astrometry. Today, I am going to go over the techniques of radial velocity, transit, microlensing, basically all of those except for orbital brightness modulation. So I will talk about each one of those in specific. But so what is this plot? Why am I showing this to you? Well, I'm showing this to you because it's one of the things, or one of the examples of why stellar systems are much weirder than we even anticipated. Again, this is mass in Jupiter masses. So anything that's over here along this line has a mass of one Jupiter. 10 times. This is a log plot, so this is 10 times the mass of Jupiter over here, 1/10 of the mass of Jupiter down here, and this is the orbital period in days. So here on the Earth has an orbital period of 365.25 days. If you were to plot the Earth on here, the Earth would be right about let's see, right about in here. The solar system objects are not put on there, are not on this plot. This is only exoplanets. But if you were to plot the Earth, it would be somewhere in this neighborhood. So obviously, we're seeing a whole lot of massive planets very, very close in to their host stars. And again, because if you remember Kepler's laws, it's basically that the orbital period is proportional to the semi-major axis, or distance away from the star. P cubed, or P squared equals A cubed. Period squared equals semi-major axis cubed. And so you get just a whole lot of Jupiter mass planets really, really close in. And also, on top of that, well, I'll get into that in a moment. But what I really want to point out to you, what I really want to bring your eye to, is there seems to be this weird structure to it, this really weird structure to the data, where you have this sort of line, this sort of cutoff here. And so when you're a scientist, you look at this data, and this is no longer small, or what we would call small number statistics. This is a robust data set. Like I said, this is roughly around 5,300 data points. So you have lots of data here to ask questions like, what am I looking at? Is what I'm looking at an actual picture of reality, or is something else going on? Because if you take this plot at face value, what this is basically telling you is that planets do not reside, low mass planets do not reside in long orbital periods. They do not reside in long orbital periods, periods of years. And there seems to be this sort of weird cut, or this sort of diagonal trend, or you can almost draw a line to basically, kind of show a cutoff, that there might be some kind of weird physical cutoff as to why correlation between the mass of the planet and the period, or where it's located in the solar system. But, and you can ask yourselves, is that real? Is there a physical reason for why that is the case? And the answer to that question is we don't quite know yet, because of something known as a selection bias. A selection bias is when your data is affected by how you obtained it. What I mean by that is one of the issues that we have with exoplanet science is really a lack of resources. And what I mean by that is to be able to utilize these methods, these radial velocity methods, these transit planet methods, we have to be able to, we don't have the resources, or let me back that out. We are limited in our resources to look for these objects over long time periods. So, for example, Kepler, the Kepler satellite, was only in orbit. Its mission was only about 3 years long. So, if it start looking at a star from day one all the way through to 3 years, it would not detect a planet that has an orbital period of 4 years. So there would be no way for Kepler to see it. So that's what I mean by selection bias, is that right now our methods are very keen on being able to find object or planets that have orbital periods that are very short, because the amount of time that we've looked at these objects with any kind of precision is rather short. We just haven't looked long enough. So there could be massive planets. There could be massive planets that have orbital periods of years, which would be kind of in line for what we see here in the solar system. So it could be that this portion of the graph, which seems to be sort of devoid of points, could it be devoid of points, or is it that we just haven't had the resources to be able to observe these, say, low mass planets, Earth-like planets, possibly orbiting stars on orbital periods of 10 years or 15 years or more? Do those planets actually exist, or have we just not been able to observe them yet? So when we look at these things, scientists have to keep in mind that there may be biases baked into the data based on the observational method that they were using. So getting back to on topic of the of this, why the subject of exoplanets basically revolutionized our understanding of solar system formation. Let me show you. Share screen. What we found is, if you go through these plots, so again, the main point, takeaway point with the mass period distribution is that we find a lot of massive planets that are very, very close into their host stars. We don't see that in the solar system. If you scroll down, you'll get to this plot over here, which is eccentricity versus period. So again, like I said, all the planets, these are planets. These fit the definition of planet. They are massive enough to be spherical under their own mass, and they are orbiting around their host star. What we can see is that for our planets, the eccentricity of our planets is almost exclusively very, very low, less than 0.1 for all 8 planets. But what we find here is that the eccentricity of exoplanets can vary significantly. We have found exoplanets with eccentricities very, very close to 1. These are planets that are on basically cigar shaped orbits around their host stars. There is nothing even remotely similar to that in our solar system. While we have objects like comets and asteroids, for example, that are on highly eccentric orbits, they are nowhere near as massive as these planets are. Again, a lot of these planets are Jupiter mass or higher. So we have planets that are not only much closer in than we would have expected, we have planets that are their orbits are very, very eccentric. They're not circular really at all. And if you keep going, although, oh, they don't have it on here. If you also look at the inclination, if you were able to plot up, and you can actually do this yourself, there is a way to actually manipulate that data and create your own plots. If you plotted up the inclination versus the period, you would see something very similar in that there is a very high, very large population of planets that have extremely high inclinations. They're not coplanar. They don't all lie in the same plane. And even weirder is that there are certain exoplanets that we have found, which are orbiting retrograde. So if you remember, to go back from the previous lecture, I said that when you look at the rotation rates, all of the rotation rates except Jupiter, or except for Venus and Uranus, are prograde. They all go around counterclockwise when looked from the north. And all of their orbits are prograde. We have now found planets, exoplanets, where the orbit is actually in retrograde. The orbit goes around in the opposite direction that the star spins. So, again, no expectation of this anywhere with the NICE model, with the model that we had constructed in order to figure out how the solar system came into being. So all of this data now. So now we no longer have one data point. We have 5,000 data points. So whatever model we come up with has to be able to explain all of these different systems. And I'm not even really going to go into, if you look at the density versus mass, or density versus radius, what you'll find is that there are potentially worlds out there we don't even know, or we have no. There are worlds out there that we have no example of within our own solar system. For example, there are worlds that we believe are almost entirely made out of water. So imagine Kevin Costner's really bad movie as a reality, where you have these worlds where basically the crust or the surface is ocean water that is tens of kilometers deep, all the way around. There are speculation that there are worlds that are just almost entirely made up of water. There's also wild speculations about diamond planets that have the density and the density or the characteristics that would indicate that the planet is primarily made up of carbon under tremendous pressure. And if you have carbon under tremendous pressure, you have diamonds. So, but my take home, or the point that I'm trying to make, is that once we started finding these exoplanets, our basic assumptions of how the solar system came into being really had to be challenged. Now, how is it that we found these things? How is it that we found these exoplanets? Well, let's start off with the first one. This is astrometry. Well, first off, actually, let me back up a second. Something you need to keep in mind is something known as the center of mass, or more properly known as the barycenter. The barycenter is the point at which something orbits. Now, we naively think that some folks naively think that the sun is in fact fixed in the solar system, and that the planets all revolve around it. That's actually not the case. It's actually a lot more complicated, or it's more complicated than that. But let's simplify it down to two things. Again, in the previous lecture, I mentioned that the vast, almost entire store of mass is locked up into two objects, the sun and Jupiter. So if we look at the sun and Jupiter, Jupiter does not orbit the center of the sun. Jupiter orbits the barycenter of the Sun-Jupiter system, or the center of mass of both of those objects, which is located not in the center of the sun, but off center, basically close to the surface of the sun. And so while Jupiter goes around in its orbit around this center of mass, so does the sun sort of wobble around that center of mass. And so the sun actually is not fixed in space in terms of if you were to take a field or a frame of reference of the solar system, somehow come up with define a frame of reference of the solar system, the sun would actually change its position over time based on this orbital motion. Now, when you start adding in all the other planets, things, like I said, it gets really, really chaotic. Trying to understand the orbital dynamics of an n-body system or a multi-gravitational body system is not an easy thing to do. Actually, you cannot do it explicitly. You have to do it computationally. And in some cases, the center of mass of the entire solar system, or basically the point at which the sun orbits around, actually lies well outside the sun's surface. So it wobbles fairly significantly. Now, why am I bringing this up? Because this is a crucial point for a number of these detection methods. Basically, well, really two detection methods that I'm going to be talking about. The first one is the astrometric detection. So what you saw there was, again, the planet and the sun, or a star, moving around a common center. So the star is wobbling. So what we're seeing here is if we were to detect a planet astrometrically, what we would do is we would look at a particular star and we would measure the distance of that star to other stars, basically reference points. The more, the better, because we don't know a priori if any of these stars are undergoing any sort of astrometric effects themselves, any sort of gravitational effects which are causing them to shift around. But the assumption is that if you have a lot of these points, those motions, if they exist, those gravitational motions, if they exist, are not correlated. So they're all going to basically they're randomly cancel each other out. So the more reference stars you get, the better. So, but the basic idea is that you measure the distance of the star to these reference points. And hopefully you can see as the star wobbles around, those distances are going to change. And from that, you can then plot what that star's position is on the sky. And from there, you can characterize the orbit of that star. And then you can walk back and figure out, all right, if the star is moving around in this orbit, then there must be a planet of this mass and at this distance away from the star, causing it to follow along in that orbit. And that is an astrometric orbit. As far as I know, that is the astrometric exoplanet detection method. You are literally watching the star move in space. As far as I know, there have been, actually, I would have to look it up. Last time I looked at this, the astrometric method was a theoretical method in the sense that it had not actually found anything yet. You have to have very, very precise observations to do this. You have to have an incredibly stable telescope, optical system in order to weed out all of the other fluctuations or all of the other things that may be making the star appear to move on your CCD camera. So you have to have a very stable, very precise instrument in order for this to work. But from my understanding, over the last couple of years, they actually have gotten this method to work on a couple of, I wouldn't say more than half dozen stars. If there are more than 6 stars astrometrically determined or found, I would be very surprised. Next one is what is known as direct imaging. Now, direct imaging has thrown another wrench into our understanding of how planets form. Now, when we look at planets, I often get asked, have we actually seen any of these planets? And for the most part, the vast majority of these 5,000 planets, no, we have not directly seen them. But but there are a few that we have. Oh, I just saw Judy's question. Have we detected exoplanets in a binary star system? We have. Actually, there are two ways, two types of binary systems that we have found a exoplanet around. The first one, not first one, but the best example I have is 55 Cancri, A, big A, not little a, but big A, the primary star in a binary system. So 55 Cancri, or basically the 55th brightest star in the constellation of Cancer, is actually two stars very close to each other, orbiting around a common center of mass. One of them we call A, big A, and the other one we call big B. We found a friend of mine, Casper von Braun, found a planet that is potentially habitable orbiting around 55 Cancri A. And so it got a lot of press about being Tatooine because they would be basically two stars in the night sky, although it really wouldn't work that way. But anyway, yes, so you can have two stars that are well separated, and you have planets going around one star and maybe planets going around the other one. We don't know. At least we don't have evidence that we have not found yet. We have not found two stars in a binary system where both stars show evidence of planetary systems. The other type of binary system, which I think is way cooler, is you have these two stars that are, I used the term well separated before. That's very subjective. But in this case, you have two stars that are not well separated, and then you have a planet orbiting around both of them. That which we call that a circumbinary planet. We have found evidence. We have found a couple of examples of that. That would be much closer to the idea of a Tatooine type planet. Whether or not such a planet could be habitable, who knows? Habitability is a open question in and upon itself. But yeah, so there are two different types of exoplanets and binary systems, and we've detected both. We've detected examples of both systems. Hopefully that answers your question. The main challenge for finding exoplanets, or actually directly imaging them, being able to see them, is the brightness difference. It's like looking at a firefly right next to a flood lamp. The amount of light coming off the star swamps the amount of light that is coming off the planet. The planet itself is going to have a certain amount, is going to emit a certain amount of light based on its body temperature, its heat. But again, the star is so much hotter than the planet that the light from the star is going to swamp it. But there's a way to get around that, and that is by using something known as a coronagraph. And really, it's just simply a matter of putting a shade or putting an object or putting an obstruction in the orbital path or in the optical path that literally blocks out the light of the host star. If you can eliminate the light from, or at least a good fraction of the light from the host star using using a coronagraph, then you can look at the environment around that star, and you can see whether or not you can find little bright points that are orbiting around at a pretty far distance. Now, here you have yet another problem with selection bias. You can only block out the light. So when you block out the light, you're also blocking out on any light that is coming from the close-in region of the star. So basically, this method is sensitive to planets that are far out. And what I mean by far out are tens of AUs, if not hundreds of AU. So actually, let me see if I can quickly pick this up. Full halt. Nope, that's not what I wanted to do. Yeah, that'll work. Should have been better prepared. There's a great there's a one of these that is an actual motion of real data. It's really really cool. It shows multiple planets. I will figure out a way to get that back up. Present. The first one of these, the first example of this, of a directly imaged planet, was Fomalhaut B. And what we find is, again, we have this. The Fomalhaut is this star in the center, and we knew previous to this, based on other observations, that it had what we call a debris disk surrounding it. This is not a full planetary forming disk, as I'll describe next lecture, but really just kind of a disk that has a lot of asteroids, a lot of comets still in it. We knew that disk existed, but when we blotted out the light of the star, what we saw was we saw a little bright point, and then when we went back and looked at it again 2 years later, we saw that point had moved relative to Fomalhaut. And so what we're seeing, and what this is basically the trick with directly imaging planets, is we have to block out the light of the star, see if there are any faint objects that are close to it, and then look at it over time to see whether or not we can see those planet or that object move in an orbit around that sun. If not, if it doesn't move, then chances are that it's just it's an alignment, a chance alignment, or chances are that it's an alignment where you have a very faint star in the background, just being in the line of sight of the star, of your target star in question. But if that star moves, and particularly if it moves and you can calculate an orbit around it, that gives you more evidence to suggest that this is in fact a planet going around another star. With the nope. With this method, like I said, the wrinkle that got thrown in was that our furthest planet is Uranus at roughly 30 AU. With directly imaged planets, we're finding planets that are very close to, or that are tens of times the mass of Jupiter, that are 50 or 100 or 150 AU further out. Again, a massive planet where we did not expect it to form or to exist. So we have found massive planets very, very close to the star, to their host stars, and massive planets really, really far out. Again, we don't have an example of that in our own solar system. We had no idea that was a thing until we discovered this. So that's direct imaging. Next one is gravitational lensing. Now, gravitational lensing is a little weird, and without really going into relativity overly much, what I will say is that space is the fabric of space. We refer to that as space-time. General relativity tells us that space-time is curved due to the presence of mass. And that curvature is going to change the direction that light travels. And so what happens is that if you have a star moving behind, or if you have a star moving in front of, sorry, I'm confusing myself for a moment. Yes, If you have a star that is moving behind some kind of mass, say another star, or more than likely a galaxy or a cluster of galaxies, what you're going to see is that as that star goes behind it, as it moves with its own proper motion, as it goes behind it, the bending of light is going to cause that light to flare like a lens, and it's going to cause that light to amplify. And so that's what this is over here, is that the light coming from the star is going to essentially be focused like a lens, and it's going to cause that light to brighten significantly. That is what we call a micro-lensing event, is when the brightness of an object, brightness of a star, significantly increases over time, over a fairly short period of time. That is only if you have a single star. But a planet also has mass, and it's also going to cause gravitational lensing. And so when we see those events, we see those as... So if we look at this light curve over here, if we were looking at this particular object over time, again, this takes a long time in order to find these. We look at the light of the star as it changes. If it just was a single star, then it would just have this sort of Gaussian main peak. But if there is a planet massive enough so that it will lens the light in itself, you'll get this little blip, this sudden amplification, very, very slight amplification of light superimposed on that much larger amplification of light. And that is a microlensing. That is the microlensing detection event. I'm going to put on my honest hat here, honest scientist hat. I don't really care for this method. The reason why I don't care for this method is that one of the strengths of the scientific methodology as a philosophical principle is repeatability. Is to be able to look at it. If you say that you detect a planet going around a star, then in my mind, that observation needs to be repeatable. Someone else needs to be able to come by and say, "Oh yeah, all right, I'm going to use my setup and see if I can detect a planet going around it," and also, and probably more importantly, use a different technique to find that same planet. That's one of the real ways that a planet goes from a candidate to confirmed, is if you can identify that its existence via two different detection methods that are independent of one another. With microlensing planets, you can't have that, just because of the nature of this phenomenon. Essentially, you have a star that is just serendipitously passing behind a massive object. It's not repeatable. It's not going to come back around. It's not like it's orbiting around that mass, unless there just happens to be, and this is going to be astronomically unlikely, another mass that it can get lensed by. It's not going to happen again. And this is a star that is, generally speaking, so dim that you're not going to be able to look at it photometrically with any sort of precision, with the precision needed to find a planet. And you can't look at, and you're definitely not going to be able to do it using spectroscopy, using the radial velocity method. So while this is officially a planet detecting method, I don't particularly put a lot of stock in planets discovered this way. All right. This is the Doppler. Now for the two workhorse methods. So here we're looking at the light from the star, and this down here illustrates, basically, is a gross exaggeration of what the color, the wavelength of that light looks like from the observer. So as it's coming at me, you can see that the light from the star becomes bluer, the wavelength gets shorter. As the star moves away from me, the star gets red shifted, the light becomes redder. Now, how do we get a planet from that? Well, based on the amount of the wavelength shift, basically the amount of based on the amount of shift from the short wavelength to long wavelength, that tells you how fast the star is moving. If something is moving a larger velocity, or a planet or a star that is orbiting faster will have a larger redshift associated with it, redshift change. So the larger the redshift change, the faster the star is orbiting around. The faster, and in order for the star to be moving at a high rate of speed, there needs to be another body. Just in general, in order for that star to be wobbling at all, there needs to be another gravitational body in the mix. The more massive that body is, the more it's going to literally throw its weight around, and it's going to cause that star to move faster. So we can use the velocity of the star to infer the mass of the planetary body that is orbiting around it, the exoplanetary body. We can also we've been using this technique for a very, very long time for binary star systems. A lot of stars that are orbiting around a common center. Most stars in the universe are actually coupled in some way. They're binaries, trinaries, or multiple systems. And we find a lot of these stars using the Doppler technique. The reason why it took them until the mid-90s in order to find planets is because, again, going backwards, the lower the mass of the orbiting body, the other body, the companion, the smaller that shift. And so it took until the mid-90s before our technology got good enough that our precision became fine enough for us to be able to measure such a small difference in the redshift of these stars. Now we're getting to the point where we can actually measure. We can measure the redshift of a person walking, moving at a walking speed, like 2 meters per second. Now it's actually kind of nuts. So that's the radial velocity method, is by using the redshift and blue shift of the star to calculate its velocity, its orbital motion, and from there you can infer the mass. Now, the big workhorse method, the other big workhorse method is transiting, which I've said quite a bit. In this case, we are looking at the light of the star, and the light that we're seeing amounts to both the light of the star and any light that the planet is contributing in any way. And we look at that star over time. And for the most part, if the planet is not crossing in front of, the light of that star is going to be pretty constant. But as soon as that planet crosses our line of sight or transits across the disk of the planet or disk of the star, the light is going to decrease by a certain amount. And that amount is going to depend on its radius. The larger the planet, the more of the light that is going to be blocked out from the sun or from the star, the deeper that dip it's going to be. And so the transiting method tells us about the radius of these planets. We can also do a little bit of gymnastics to make an inference about the mass of the planet. But the Doppler technique, oops, wrong one. This technique gives us the mass of the planet. This technique gives us the radius of the planet. If you can look at the same, again, power of science, if you can look at the same system using both Doppler and transit, not only can you confirm that, yes, the what we're seeing, the observational effects that we're seeing, the changes in the velocity of the star and the change in the brightness of the star, those are actually being caused by the presence of an exoplanet, but also you can get the mass and radius and density. And that's when we can start talking about, is it a Jovian planet? Is it a planet primarily made of gas? Is it a terrestrial planet, a rocky planet like the Earth, or a weird water planet or diamond planet? So when you see stories in the news about exoplanets and they talk about them being terrestrial or being Jovian, the reason why they are able to say that is because they have an estimate of the planet's mass and radius, and therefore its density. Because again, if you remember from the Jovian planets all have very, very low densities, very, very close to the density of water, whereas the terrestrial planets all have densities much, much higher, about 5 times higher than the density of the Jovian planets, primarily the density of iron and nickel, or combination of iron and nickel. And so, yeah, so those are the major methods used to find exoplanets. And so I've made a lot of business. Hair. About how exoplanets have made things weirder, or really challenged our understanding of how the solar system came into being. Well, 55 Cancri. There you go. There's 50 Cancri. Well, this is F. Well, this is a basically a cartoon. He found Casper found E, but anyway, this is an example of what I was talking about in terms of the range of eccentricities that we found with the exoplanets. So the eccentricity of the Earth is 0.017. The eccentricity of 55 Cancri F, another planet in that system, is even smaller than the Earth. It's even almost perfectly circular. And then you have HD 80,606b has an eccentricity of 0.934. So we are finding through these exoplanets planets we had no idea of they could possibly even exist. So the major addition, what this led to, is it led to our understanding that when the planets are forming in the disk, and again, I'll go into the specifics about this next time or in the next lecture. But as these planets are forming, they're not doing so, pardon the expression, in a vacuum. They are not doing so just as solely small individual objects. This is a big chaotic system. There is material all over the place. There's mass, there's gas, there's dust all over the place as these objects are forming. These objects themselves have mass, and so if these two protoplanets are starting to come close to each other, they're going to gravitationally interact, and that's going to cause those orbits to move. And so you get this idea of migrating planets. And so a planet can change its position as it's forming based on its interactions with the disk. Basically, friction within the disk can cause the planet to migrate inward. And so that explains the 51 Pegasi b planet, in that we suspect that planet formed in the outer part of the solar system, near where Jupiter is now. And then because of the characteristics of the disk it formed in, it lost a lot of its angular momentum, a lot of its orbital energy due to interactions with the disk itself, and it kind of spiraled inward until it reached a stable orbit very, very close to its host star. We at this point, we believe we have found evidence of stars that have eaten some of their planets, that some of these planets don't survive this migration. They actually spin all the way down in and get destroyed, actually fly into the star itself before things gravitationally stabilize, essentially. Also, you can have, again, if you're talking about planets that are orbiting, coming close to each other, protoplanets that are coming close to each other, or planets once they've formed and are just really, really young coming close to each other, they can scatter. They can gravitationally fling them around in their stellar systems. And that explains, we believe that could explain the planets that are really, really far out, those directly imaged planets that are 1,000 or that are 100 AU out. But we definitely think that it can explain why we see planets that have such high eccentricities and high orbital inclinations, is because these planets have been disturbed through interactions with other planets in that planetary system. And also as a consequence, and there has been a suggestion that we have found these, although again, I tend to be a bit more skeptical about this, but there is the possibility of rogue planets, of planets that are get ejected from their from their host systems, and you have a planet just freely passing through space that isn't orbiting around a star. There has been some evidence to suggest that we have potentially found some rogue planets, but again, like I said, it's in my opinion, the evidence is not strong enough. But I am not the entire community, so there's that. All right, and with that, I already talked about alien planets. I'm going to leave off on the topic of habitability until the end of basically until the end of the semester, where I just basically talk about life in general, but where I'll talk about habitable zones. But yeah, that is all I have for y'all today. I hope that was clear. I hope that you were able to follow my explanations. I hope I have taught you something that you hadn't learned before. And again, you found this to be entertaining or fun. So yeah, now I'm babbling. All right, I need to go off and take care of some stuff before evening under the stars. Again, we have a public night here at our observatory. Plug in this. I'm just going to keep plugging this. Our speaker is Dr. Hakeem Alusier. He is going to be talking about the sun. It starts at 7 p.m. Eastern Standard, or I guess that would be 11 p.m. UTC. So yeah, don't forget to like, share, and subscribe if you like this sort of content. And if you'd like to support our endeavors here at the observatory in terms of public outreach, we're having a lot of, we have International Dark Sky Week coming up, so we're doing some events next week in that regard. Near the end of the month, we've got Earth Day, so we're doing a lot of events in terms of public outreach with our planetarium for Earth Day. So if you're interested in helping us with those, financially helping us with those endeavors, please consider becoming a Patreon or sending me money through PayPal. So, all right, e-begging completed. And so with that, I will ask if there are any questions that you have. And if not, then I will bid you all good day. Thank you, Bellywood. I appreciate that. Said, I hope this was clear. I really love Exoplanets. I really love Exoplanets. It is a fascinating subject to me. It was one of the things that originally got me into astronomy. I then pivoted to more cosmology when I actually started becoming an undergraduate. Realized astronomy or cosmology was way harder than I anticipated, so I moved on to young stars. But it's always been a kind of a fascination or a good subject or a fun subject for me. All right. So yeah, if you have any questions, again, put them in the comments. If you're watching this later on, please put them in the comments. I try to answer those questions or answer those comments as soon as I can. So with that, I bid you all good day. Clear skies and peace out.